Welcome back. The objectives of this video are to define polynomial functions. We will look at maximum and minimums of those functions, and we'll also explore even and odd degree polynomials. Below is our formal definition of a polynomial function. A polynomial function in some variable x is said to be in standard form when the terms are arranged by degree in descending numerical order. A polynomial function p of x, where n is a non-negative integer, is defined like this mathematically. You might be more comfortable with something like p of x equals 3x to the fifth plus 7x to the fourth minus 2x squared plus 7. We don't have an x cubed term and we don't have an x term, but this would be an example of a polynomial function that has degree 5 and it's in descending order of degree. A turning point of a function is a point at where the function actually turns from maybe increasing to decreasing. So it changes direction from upwards to downwards or downwards to upwards. So let's take a quick look at maximum and minimum. For any function f, there exists an interval between a and c that contains b, so that for all x can equal b in the interval, well, what does that mean? In short terms, f has a local maximum when f of b is greater than f of x, and f of b is called a relative or a local maximum. Looking at our graph on the right, we can see these points up here would be considered a local max. Actually, we could probably call them an absolute maximum because there's no y values above 5 here. So both of these points would be an absolute max. But if we took a region, if we just looked at like between 1 and 3, this would be a local maximum. Whereas this point here at the origin, where it turns direction at this turning point, this would be a local minimum. If we look between like -2 and +2, this is the minimum y value. That would be a local minimum or a relative minimum point. Example 1 asks us to use the diagram here at the right, and it says on the graph at the right, shade the intervals of increase in green and the intervals of decrease in red. So where our function, as we read from left to right, as x's increase, we want to see where y's are increasing. So that one is in green. That's going to be an interval of increase. And also here, starting at 2, -6, and going off to infinity is another area of increase. The interval of decrease, the function is decreasing, our y's are decreasing between x's of -1 and +2. And it asks me to sketch that in red, so we'll put that in red. I've completed the intervals of increase and decrease. We're increasing between -infinity and -1 inclusive, and including 2 to +infinity. And our function is decreasing between x values of -1 to 2. So these are the x values that we would write in there. I also took the liberty to label the local extrema. Our local maximum occurs at the point -1, 6. So we might say our local maximum is 6. And our local minimum is at 2, -6, or our local minimum is at -6. In example 2, they ask us to use our graphing utility to determine the relative maximum or relative minimum of the function. State the intervals where the function is increasing or decreasing, and what is the connection between the relative extrema and the intervals. So we've got a place here to sketch our graph. We're going to do some, it's going to be just approximate. We don't have to label our x and y axis. And we'll put our function into our graphing calculator. So take a second, grab your graphing calculator, and I'll show you how to get this started. So I've put our function into y1 under the y equals menu. I've got my plots off, and just that one is highlighted. Negative 2x to the fifth plus 10x squared plus 16x. I'm going to go ahead and graph this into the standard window and see what that looks like. So I'm going to go to Zoom Standard and just graph that in the window that's from negative 10 to positive 10 on the x and y axis. And we'll take a look and see what our graph looks like. So I don't have a complete picture of the graph in here, so I might adjust my window a little bit so I can see what's going on. So I will go back to my window. My x's, I can actually consolidate those and make that a little bit smaller. I can probably go from negative 6 to positive 6, but I need to go quite a bit higher on my y-axis to look at my y's, and I'm going to head up around 50. I'm not going to count by ones though. I think I'll just count by fives on the y-axis. Let's take a look at that graph. And that gives us a much better picture of what is going on. So we can see here we've got turning points. We've got a relative maximum point here on the right. Looks like that's somewhere between 1 and 2. And we have a minimum, a relative minimum. A turning point here that looks like an x value of negative 1 and a y value probably around 5, a little bit more than 5. So let's find out exactly what those are. We can use that by going into the calc function and finding maximums and minimums. So our first question says to look for a relative maximum. And we can see here we've got a relative maximum somewhere between 1 and 2, it looks like. So we'll go to second calc. Number 4 is a maximum, so we're going to find the relative max. And it's asking for a left bound. So we're flashing right here, and our cursor is to the left of that relative maximum, so we can select that point. And we'll cursor past our turning point to the other side, and we're going to choose an x to the right of that maximum and hit enter. So our calculator will hunt between these two x values for a local maximum. It's asking us to guess. I'm not going to bother, and I hit enter, and sure enough it gives us a relative maximum point, an x value of 1.457, 1.458, and 31.409. Now I'm going to find the relative minimum point. Go back to my calculator, second calc, find the minimum. It's asking for a left bound. I've got a cursor over. I've cursored to the left side of that minimum point. I hit enter. Calculator asks for a right bound. I cursor past that, hit enter. It's going to hunt between those two x values for a minimum value. I'm not going to make a guess, and it gives me the minimum point at negative 0.688 and a y value of negative 5.96, and that's about what we thought that would be. We have enough information to make a sketch of our function with our max and min, so I will go ahead and sketch that. So I've drawn our function, and I've gone ahead and labeled the turning points. Our relative minimum and our relative maximum are labeled on the graph. We can see that our function increases between the minimum and the maximum. So I've written that in interval notation. It decreases leading to the relative minimum, and then it decreases coming out of the relative maximum. And I've written that in interval notation as well. And our connection here is that the relative extrema, the local min and the local max, are the turning points of our graph. In example 3, they tell us that between every two distinct real zeros, or x-intercept, of a non-constant polynomial function, there must be at least one x value that corresponds to the maximum or minimum. So you can see here we have some x-intercepts on our graph, and between those x-intercepts we either have a minimum or maximum value. So they ask us to determine the zeros of the function. We see they're at -3, 0, and 4. B says state the value of x where the local maximum or local minimum occurs. We can estimate that from our graph. It looks like our local minimum occurs at an x value of maybe a little bit after or negative of -2. It looks like about -2.1 and about -3.75. And it looks like a local max occurs at the origin, so that's easy to see. And then we have another local minimum right around 3, maybe 2.9 or so, and a little bit more negative than -8, maybe -8.1. We're going to have our calculator tell us exactly what those are. So I enter my function into my graphing calculator. I can steal my window from the problem that they gave us. It looks like our window ranges from, we could use this, looks like we could use the standard window. So when I graph this, I'm just going to go zoom, standard, and go ahead and graph my function. I need to find a couple of local minimums and a local max. So second calc, I'll find the minimum. So I found my left bound. I'm about to find my right bound. Don't go too far to the right, otherwise you'll capture that other point there. We'll hit enter. We'll hit enter again, and we find our minimum is -2.103 and a y value of -3.632. We can go ahead and find the local maximum. Let's go ahead and do that. Go second calc. We'll find the maximum. It's asking for a left bound. I got it. I'm going to cursor over to the right of that. I'm going to right bound. And that is essentially 0, 0. That is essentially the origin. And then finally, we'll go ahead and calculate our final minimum point. There's my left bound. Cursor past that to my right bound, and get my minimum and maximum, and then I can transfer that over to my answer sheet. Back to our notes. Our local maximum was at x equals 0. Our minimums occurred at x values of -2.103 and 2.853, and the y values for the -2.103 was -3.632, and the y value for the 2.853 was -8.197. So I had pretty good guesses on that. We did eyeball the zeros. We could have used our calculator for that. You might have spotted that on the calculator. When I went to second calc, it asked for the zeros. Option 2 says 0. So we could do the same process. We want to calculate the zeros. It wants a left bound and a right bound. I've got my left bound. My cursor past it. I got my right bound. And it gave me the 0. The x-intercept is at 4, 0. So my eyeballing was probably correct there. In our previous sample, we looked at relative maximums and minimums. In this case, we don't have a continuous function. This one doesn't extend down to positive infinity. So this is going to have an absolute maximum and an absolute minimum. Now keep in mind, those values are the y values for the absolute max and min. So we can see at f equals 1, when x value is 1, our maximum y value is 3, and our absolute minimum here occurs at -3, and the y value is -5. Defining relative or local extrema, they are the y values on the graph of a function where the function changes from increasing to decreasing, so those turning points. An absolute or global extrema are the highest or lowest y values of the function over a specified domain. Example 4 asks us to label and identify the relative and global extrema for each of the functions. So they're asking for relative max and relative min, and absolute max and absolute min. In A, our absolute maximum, our y values are heading off to infinity. Our minimum, the y values are heading to negative infinity. So there is no absolute max or absolute minimum. It appears we have a relative maximum here at an x value of 1 and a y value of 5. And we have a relative minimum at an x value of 3 and a y value of 1. So I filled those out and put those ordered pairs in. In sample B, let's take a look at this. Both end behaviors here, we'll talk about end behavior in a few minutes. But the end behavior here, it looks like both of these are going to negative infinity. So there's no absolute minimum, but there is an absolute maximum. This point here up at what appears to be 2, 8 is our absolute maximum. So we have a y value of 8. That's our maximum. It appears we have another maximum point here at 3, 0. And this is also a relative maximum, our 2, 8. Although it's an absolute max, it's also a relative max. And then a relative minimum point at negative 1, negative 2. So I finished labeling the graph with our maximum ordered pairs and our minimums, and then our relative max and mins. I think you've got the hang of this, so I'll let you do problems C and D, and you can bring those to class. And that wraps up this video on introducing polynomials and the maximum and minimums of functions. And you'll get some more practice with this when I see you in class.